Okay folks, our last video in this very short section on equilibrium, know how to apply the Chatelier's principle. So hopefully this is very familiar to you from your other chemistry classes. So we'll just talk about this briefly. So recall in Le Chatelier's principle, if a change is imposed on a system at equilibrium, the position of the equilibrium will shift in a direction that tends to reduce that change. So here I've just got this simple generic reaction, A plus B in equilibrium with C plus D. And we can now play this game like what happens if we add more reactant or we remove more reactant. So if I add more reactant and the system is already at equilibrium, because it wants to preserve the value of the equilibrium constant, right? Let's write that down, and we'll do it just simply in terms of the concentrations, using the approximate way you did it in general chemistry. This A and B is going to shift the reaction to the right. So that reactant has to end up becoming more product. However, if I remove more reactant, now I've got a vacancy over here, so the reaction will shift in the opposite way. Again, we have to preserve the value of the equilibrium constant. So now similarly, if I add more product, it's just the same as removing reactant. And of course, if I remove more product, it's just the same as adding more reactant. Again, all of this preserves the value of the equilibrium constant. Okay, so what if we change the volume or pressure of the system? Well, if we change the pressure by adding an inert gas, nothing happens, right? That gas is not involved in the reaction. But if we change the pressure by changing the volume of our container, and specifically for a gas phase reaction, that will affect the equilibrium position. And we've got to remember that concentration, right, is amount per volume. So if we reduce the volume, we have to reduce the amount. And if we increase the volume, we have to increase the amount. But the way that shifts, whether it be to the left or to the right, is entirely dependent on the reaction. So for example, let's suppose this simple reaction of A2 becoming 2A. So we can see on this side of the reaction, we've got one thing, and on this side of the reaction, we've got two things. So quite simply with this reaction, if we're at equilibrium and I reduce the volume as shown here, the reaction is going to want to shift back to the side that minimizes the number of moles because we minimized the volume, right? We've got to preserve that ratio. However, if we had a reaction in which the opposite was true, so maybe in the reaction it goes 2A goes to A2, right? And we do this same thing where we decrease the volume, then obviously the reaction will shift in that direction. Again, keep in mind we've got to preserve these ratios, okay? So, and then the final thing we'll talk about is changes in temperature. And it's important to note that this is the only shift that will result in a change of the equilibrium constant, because as we recognize, the equilibrium constant is temperature dependent, right? So one way we can write that is with respect to the Gibbs free energy. Another way that we can think about that, if we integrate this equation over the limits, then we arrive at this Van 't Hoff equation, which would allow us to calculate the new value of the equilibrium constant based on some change in temperature. Okay? So we can think of this very much in the same way as the other shifts. So for example, if I have an endothermic reaction, we know that energy is a product, right? So if I increase the temperature in an endothermic reaction, it's going to want to shift it over to products. Conversely, if I cool down an endothermic reaction, so we'll say, I'm going to say add heat, right? That's actually going to look confusing. Let's just write add heat. Okay, let's try that again. So add heat in this endothermic reaction, it's going to want to shift it that way. But of course, if I remove heat. So if I make my endothermic reaction colder, it's going to favor reactants. So now, similarly, if I think about this exothermic reaction, if I add heat to an exothermic reaction, it actually shifts it back to reactants. However, if I remove heat from an exothermic reaction, it's like I've removed product, and that's going to make it shift more towards the products. Okay? So in other words, exothermic reactions run more efficiently at colder temperatures. They produce more product. So here's one particular example that I wanted to look at, solubility, as this relates kind of directly to what we were talking about with our mixtures and our activity. So if we think about what drives solubility, that is the KSP equilibrium expression, right? And so recall KSP is given by the following reaction. So we'd say calcium hydroxide is in equilibrium with its respective ions. Okay? So the more ions we have present, the larger is our solubility. And so now what I want you to notice here, it's interestingly, the solubility increases with decreasing temperature, right? So now we have to think about if this is an exothermic process or an endothermic process, right? So if by decreasing the temperature, we've increased the amount of reactants here, right? Let's think about what that's going to do. So if by removing heat, we push from reactants over to products, that indicates that this would be an exothermic process dissolving calcium hydroxide. Okay? So anytime we see solubility decrease with increasing temperature, we could then conclude that this is an exothermic solution. And I had mentioned in our previous module that it was really difficult to come up with examples of exothermic solution formation. And here we can see this demonstrates just that. Okay? So we could go through loads more of these examples, and we'll touch on some in the live lecture. That's it for equilibrium. I know it was really short, but you've talked about equilibrium in all of your chemistry classes, so I only wanted to touch on this briefly. Okay, folks, we're going to be getting into kinetics after this. I'm pretty excited about it. All right, I'll see you then.